Hello everyone. I'm Liam again. I'm just gonna show the proof of the power rule using first principles. So we've established from our previous video that this formula here is the formula for a derivative. And then for the power rule, we're gonna need to understand this. Well, not really understand it, just be able to use it, because to be honest, I don't really understand it. But it's to do with combinatorics, basically the way you can like arrange groups of items, but it comes in handy whenever you're expanding out a polynomial or binomial. So for example, say you have I'll just use x and h because it'll link well with what I'm going to do later. So say you've got x plus h to the power of n. If we were to expand that out, we would get x to the n plus n choose 1, which is our coefficient for the following term. Then it'll be x to the n minus 1 times by h to the 1. And then you would continue that on going n choose 2, x to the n minus 2, h to the 2. And then that will keep going on n amount of times. Sorry, it looks like a division symbol, but it's not. And that's basically just a way, using Pascal's triangle, it just shows a way for expanding out a polynomial of nth order. So why this is useful for the power rule. So imagine we have a function, x to the n. Sorry, let me write down f of x equals x. Ooh. F of x equals x to the n. If we're going to work out its derivative, we just plug into the formula. F dash of x is the limit as h tends to 0 of x plus h to the n minus x to the n divided by h. Now, this is just our general case for a function or a term of nth order. So this comes in really useful for just proving that any case works. So for example, I've done here x squared. This is handy, and I know it works for, I know that the formula, the power rule, works for x squared because I just take down the 2, but I want to prove that it works for every natural number n, or would it be real number n, where n is a real number. So what I would do here is I would just use this formula here, so n choose r, as well as this. So I know that if I'm expanding this out, I will get f dash of x is equal to the limit as h tends to 0 of, so we establish x to the n plus n choose 1, x to the n minus 1, h to the 1, plus n choose 2, x to the n minus 2, h to the 2, n amount of times, minus, now I'm not going to write the last few terms because they don't actually impact this proof here at all, because as you'll see, they'll eventually cancel out, minus x to the n, because that's coming from this part here, all divided by h. There we go. So working out n choose 1, I'm only going to simplify this one here. I'm just going to color it in red just to make it stand out. I'm only going to simplify this one here because, as you see here, it's got a h to the first power. So using the previous ones, we could probably confidently say that the h will cancel out. Probably confidently, that doesn't really make sense, but we know from our formula that n choose r is equal to, sorry, let me just write this bit here, n to 0, x to the n plus, so n choose r is equivalent to n factorial divided by r factorial, and in our case r is 1 factorial, times by n minus 1 factorial, because r is 1, times by x to the n minus 1, h to the 1, plus dot 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 dot, all of those other terms, and then eventually we will get minus x to the n over h. Okay, so what do we know? Well, we know from this here, so I'll hone in on this part here. So n factorial divided by 1 factorial times n minus 1 factorial. Well, what is that equal to? So let's just say we've got 5 factorial. We'll choose n to be 5. That'll be 5. A factorial is basically timesing by every positive integer below it until 1. 5 times 4 times 3 times 2 times by 1. We know 1 factorial is also just 1. 1 factorial, sorry. Times by n minus 1 factorial. Well, if n's 5, it's just going to be 4 factorial. So it'll be 4 times 3 times 2 times by 1. So those are all going to cancel out, and we'll just get 5 over 1. Therefore, what we can say is that n factorial divided by 1 factorial times by n minus 1 factorial is always just going to be n. And that works for anything. It works for any number. This works for 6 factorial because this n minus 1 factorial will always cancel out with every number below n. So that's really handy for this. So we use the limit as h tends to 0 of x to the n plus, now we know n factorial, so n choose 1 will just be n. N times x to the n minus 1 times by h to the 1 plus whatever minus x to the n over h. So we know from these ones that all of these terms after x to the n, so after n choose 1, n minus, so after this term here, we know all these terms are going to contain a h. That means that whenever we can factor out a h from them. We also know that this x to the n and this x to the n will cancel, so we'll just get limit as h tends to 0 of n x to the n minus 1, sorry, let me write a h at the front here, plus dot dot dot, and they're all going to have a h in them. So we can safely factor out a h, and therefore they cancel, giving us the limit as h tends to 0 times n times x to the n minus 1 plus some constant, we'll just do a x to the b h to the r, something like that. They're all going to contain a h still, so then we can allow the limit to be 0, therefore resulting in n x to the n minus 1. And that's our proof. It's a bit kind of faffy because like all this like junk looks really difficult, but actually like understanding that every term after the n minus 1 term will contain a h and therefore will be 0 once the limit approaches 0. So then we can confidently say that the derivative of a function of x, which is in the form x to the n, is equal, or sorry, f dash of x, sorry, write this. So if you've got a function f of x, which is equivalent to x to the n, we can confidently say that the derivative of that is then nx to the n minus 1. And then using our rules, we know that the sum of a derivative of sum is the sum of its derivatives. So that will work for every sort of, say you've got f of x is x to the 4 plus 5x squared plus 3x squared, or 3x. We know that the derivative of that is then just going to be, what is that? The derivative of this is just going to be the derivative of each of these individual terms. And now using the power rule, we know that it's just going to be 4x cubed plus 10x plus 3. And that's the power rule proof. So I hope this helped your understanding a little bit. Thanks for watching.